So now let's consider the conservation of energy with dissipative non-conservative forces. That's what the NC stands for, non-conservative. The kinetic work energy still applies whether the forces are conservative or not. And so we have still that the change in kinetic energy, Kf minus Ki, is equal to the work done by the net forces. The difference is that now we have non-conservative forces, and so the work done by the conservative forces that enter into the net forces are the difference of the initial minus the final potential energies. That's just what we did before. But now what we need to do is we need to include a term that takes into account the work done by the non-conservative forces, and that's this term right here. And so if we put the terms that are subscripted with F for final all on the left side of the equal sign, and we keep the terms subscripted with I for initial all on the right side of the equal sign, and we keep this work done by non-conservative forces on the same side as the initial, what we end up with is that the final mechanical energy is equal to the initial mechanical energy plus the work done by the non-conservative forces. And so if the work done by the non-conservative forces is less than 0, which is true, for example, if friction is present, then you can see that the final mechanical energy is going to be less than the initial mechanical energy. If, on the other hand, you have a situation where the work done by the non-conservative forces is bigger than 0, then the final mechanical energy will be larger than the initial mechanical energy. And so to take an example here, let's take the same example we did before, except now we have a mu not equal to 0 situation. And so if you write the initial, if you use this equation here, so here's the initial EPE, electric potential energy. Here's the initial GPE, initial gravitational potential energy. Here's the initial kinetic energy, and here's the work done by the frictional force. And so how would we compute this? Well, we would compute the this displacement, the flat portion of the displacement, times the normal force, which should be anti-parallel to the displacement, so that would, in other words, be negative. And then as it slid up the ramp, we'd have to compute the force slightly differently, because the normal force would change, but it would still be a situation where the frictional force would be anti-parallel to the displacement up the ramp. So you'd have negative terms contributing to this is equal to, well, the final versions of everything we have on the left side, with the exception of the work done for the frictional force. Here is the final EPE, here's the final GPE, and here's the final kinetic energy. And again, if we set the initial and final kinetic energies to 0, as we did before, and we have an initial GPE of 0, then we have 1 half kx squared plus the work done by the frictional force is equal to mgh. That's the final energy, which is in toto the GPE, gravitational potential energy. And then you solve for h, it would be 1 half kx squared plus the work done by the frictional force divided by mg. Now that this term is less than 0, the impact of that is that the m will not go to as great a height, because this much energy has been dissipated as work done against friction.